Hello and welcome to our today's webinar regarding the topic live analysis of production data. My name is Sarah Muche and I'm very pleased to welcome again so many of you to our today's webinar. I welcome very warmly also Andreas Kühne and Patrick Kaiser. Dr. Kühne is working for Analyses GmbH as lead data scientist, and Mr. Kaiser is also data scientist and part of the software development and the IoT team of EMAG. They will guide us through the webinar today. We will give you also the possibility to ask your questions during the presentation. Please use for that the webinar tool. And there will be also the possibility to discuss your questions after the webinar with our experts in the studio. Today we ask ourselves, collecting production data, now what? We will give you the answer how to generate with IoT solutions a real added value. Due to the interlinking of machines with IoT and Industry 4.0, there will be a huge amount of data produced and saved. But only by analyzing this data, e.g. with EMAG IoT solutions, you're able to identify potentials and optimizations. This is what we want to show you today. Maybe we talk today about a topic which addresses most of all the specialists behind programming. For that I want to do some advertising for us, because next week we have a webinar which presents the EMAG IoT world live from our production area at a machine. I would be happy to welcome again a lot of you next week to our production area. And today our experts will even start a live analysis with machine and sensory data and show you how fast hypotheses and optimizations can be generated for your production. So far from my side, and now I directly hand over to Dr. Kühne and Mr. Kaiser and wish you an interesting webinar.
Thank you. Welcome to our webinar on live analysis of production data. How to make the best out of collected data to enhance your production processes. Before we start, maybe some introductory words. Nowadays it is often the case that the technical optimization potential of modern production lines has almost reached its limits. Nevertheless, there is still optimization potential available in many production lines. For example, due to unexpected machine or tool breakdowns, unobserved quality problems, or inefficient production processes. Due to the emergence of IoT, we gain access to machine and production data at any time in the process. By using data analytics, one can get valuable insights into this data and can derive measures suited to fully utilize the production potential and to achieve a competitive advantage. I will now hand over to my colleague Andreas for the first topic.
Thank you, Patrick. Yeah, with this we continue to the topic, what kind of data analysis can you do in production? So we subdivided this in 3 areas. So first of all, obviously you can analyze data live during your production process. For example, to monitor your process, to get hints on if there's something going on with your production line and you have to react, and also make some little forecasts. So this is very helpful to have a transparency about your production process and to run it smoothly. Obviously, you can do analysis of historic machine data. This is one of the topics we focus on today in our live analysis. So analysis of historic machine data is very useful. For example, if you want to diagnose some problems, if you analyze your process in depth and also identify, for example, optimization potential, so how you could improve your production process. And on top, if you really know very well how your production process is running, obviously you could also do some forecasting and planning. For example, a forecast of if a user need to interrupt the machine, for example, or also of predictive maintenance cases. So this is a very hot topic now in production, because with predictive maintenance, for example, you can reduce your machine downtimes and increase your production time. But before we dig deeper into the data analysis, we want to show you some of the products EMAG is offering that enables you to do live data analysis. First of all, we have the IoT Core and Cortex, which help you to collect data from your machine and store the data from your machine. Then we have already some application, the Aetna data apps, which calculate KPIs live and show them in the Aetna Lifeline dashboard. This helps you to visualize and analyze the process of your production line, and also gives you some hints where you have to, where a user needs to do something in the machine. And then we have a condition monitoring and predictive maintenance solution, the Aetna Health Check, with the Neuron 3DG sensor that helps you to track your machine health and helps you to plan your maintenance needs. And on all of these topics we go a bit deeper now to show you what it is about them. The IoT Core and the Cortex are there to collect the data from your machine. So the IoT Core is this little IPC, what you can see in the bottom right. So this is installed in every machine. And on this, the Cortex software is running. The Cortex software is connected to the machine control, for example, to Siemens or Fanuc machine control units, and gets the data directly from the control unit and collects it and stores it in a ring buffer system. On top of it, you can also connect different type of sensors, for example, like acceleration sensors to the IoT Core and collect the data with the Cortex. But also we have some open interfaces, like we have CSV imports, but also MQTT and a REST interface that enables you to store any kind of data that you want with the Cortex. Obviously, the data is not only stored in the machine. You can also transfer the data to a higher hierarchy level, for example, per MQTT or REST for long-term data storage, so that the ring buffer system is not running out. When you have data collected, I think there's a question.
I want
Sorry.
to shortly interrupt for a question from our audience. Yes, maybe it's regarding the last slide also. Yeah, is this ready to use solution, and who can I contact for more information?
Yeah, good question. Yes, it is a ready-to-use solution. So the IoT Core and Cortex is available as option for any new machine, but also it's available for retrofit. For this, you have to discuss with your contact person at EMAG if depending on the age of your control unit that you're using in your machine. Not any of them can be connected, but most of them. So best is to contact your person at EMAG, or also in the end we show you some contact details of us, and then we hand it over to the responsible person, but it should be possible, yes. With this, we then continue to the data analysis part. Obviously, if you collected enough data, then it's very interesting to analyze the data. And for this, you have different opportunities. You can have some visualization tools like Grafana, or you do even some basic analysis with tools like Excel on your own. But often it is the case that you have some analysts or data scientists that do some programming and some data science. And this is often done with tools like Python, for example. What we developed at EMAG is the Aetna data science pipeline, which is really focused on analysis of production data. It has standardized interfaces, for example, to the Aetna Cortex, which makes it very easy to load and store data, and also like internal modules of objects of the data science pipeline. And it has also a lot of standardized modules that you can use. For example, some module for data import, some modules for data pre-processing. So, for example, that you can easily remove outliers or harmonize your data. And also standard modules to generate features, and also for modeling with machine learning models, and also for model management. This pipeline structure can be extended with custom code, for example, and therefore you can apply it to any use case. What is also very interesting about this pipeline, that there's some kind of information about your asset in it implemented, so you know that the pipeline knows what kind of machines you have, what kind of the machine types you have, and this is used, for example, to fit the individual models to the right data that is coming from the Cortex. So because not every model is designed for every machine, sometimes you have models for that only work for one machine, some other models work for one machine type, and this is all managed by the pipeline on its own, which makes you the implementation process way smoother. And one question I always get from data scientists when I talk about this: can we use the libraries that we are used to do our analysis and modeling? And the answer is yes. The pipeline is compatible to any machine learning library that is available for Python, so it's very easy to integrate. Yes.
One more question, thank you. One of our customers says we don't have anyone in our office who is specialized in data analysis. And is it possible to use and understood by everyone?
Yeah, it's a good question. Obviously, not every customer has some experts on data science or data analysis. And so first of all, a data science pipeline was designed at this initial scope for a data scientist, but we already now use this to enable like domain experts to do their data analysis on their own. So what we did then in this case, we designed some small script with defined analysis and made some interfaces where, for example, a domain expert could do some parameterization on his own. So he had some dynamic analysis which generated added value for him, but could use this flexible structure of the data science pipeline. This was a very good way how you can address also the issue or the needs of also non-experts in data analysis. Yes, so it's possible, I would say. Okay. With this, I would just mention in the end the advantages that you get in using this data science pipeline. So one of the biggest advantages is that you can just focus on implementing your analysis or task and also the business logic, and don't have to think of all the data infrastructure which is all around and spend your time on this implementation. Furthermore, you have a way higher quality of your code, or in most cases at least, because you rely on already standardized and implemented modules that have been tested several times, and all of these two combined makes it very fast that you can bring your codes from the experimentation part into production. So we managed to build an app with this data science pipeline within, I think, 3 weeks, where we already had it at a machine and tested it live, and this was very fast in terms of data science in production. Now, in the end of this little intro, I want to show you how such an infrastructure could look like live in, or could be implemented on a customer site. So what you can see here on the bottom is like 7 machines that are connected to the Aetna Cortex. The Aetna Cortex is collecting the machine data and the sensory data for each of the machines, and then sends it via MQTT to a higher level, to the edge cloud, which is like, for example, a server or virtual machine at the customer site. So it's not in the internet, and the data doesn't leave the customer side, but it's running in the edge cloud. And there we have another Aetna Cortex where the machine data is stored for a long time. And on this side also the data science pipeline is running in certain applications of the data science pipeline. There, the data science pipeline applications get the data from the Aetna Cortex, do some data analysis tasks and some forecasting, and send the results again back to the Aetna Cortex, which publishes these results, for example, for use on visualization in dashboards like you can see in the top right. And these dashboards, for example, can then be shown live in the production hall. With this, we get to the end of our introduction and go further on with the case studies. So today we brought you 2 different case studies where we want to show you how you can generate value from production data. First of all, we focus more on acceleration sensor data, which we normally use to monitor machine health and, for example, identify problems of the machine. And then later on, we continue with using production data to calculate simple KPIs like takt times or OEE, but also to perform some more in-depth analysis like a root cause analysis. With this, I hand over to my colleague Patrick for the first use case.
Thank you, Andreas. So I will now go on with our first live demo use case, analyzing vibration data or acceleration data gathered by our Aetna Neuron 3D sensors. For this use case, we will take a look at acceleration data recorded at an EMAG turning machine over time. We will visualize and analyze this data in time and frequency domain to get valuable insights and detect possible machine problems. For our analysis, we will use Python as programming language, as Andreas already mentioned. Python will help us to visualize and analyze our data in a quick and easy manner. So before we start, maybe some background information on how we use this acceleration data in our solution Aetna Health Check. Here we record acceleration data regularly and automatically, for example, once a day during lunch break. Then we have the health check process, where an algorithm assesses the machine condition or health check, or health condition as we call it, in terms of machine wear. And finally, we can visualize the machine health in a line chart to detect possible trends over time. For this, the measurement is subdivided into different parts, where each part represents an individual test regarding one of the machine axes. For example, the feed test in X direction, the feed test in Z direction, the spindle test, or even some circle test. Every individual test is analyzed individually by our algorithm. Now I will switch to my programming language, programming environment. As already mentioned, in the following live demo we will learn how to visualize and analyze acceleration data from our Etna Neuron 3DG sensor, which were collected by our data collector Etna Cortex. Specifically, we will focus on detecting so-called interference frequencies, but more on this in a second. Before we start our analysis, we first have to import our relevant modules. Here we use standard Python modules, which are freely available on the internet. We have modules for data manipulation, data filtering, or of course data visualization. So the first step would be to import these modules so that we can call these modules and work with them. Okay, successfully imported them. So the next step would be to import our data. Here we have our data in a CSV file, and I will import it now. Then we can get a first glimpse of the data. So here we can see the first 10 values of our acceleration data in X, Y, and Z direction regarding our machine axis, as I mentioned beforehand. So to analyze our data or to work with it, we first have to define our sampling frequency, which we got from the datasheet of our sensor. And next step would be to visualize our data, to gain insight into the data and identify possible patterns. And now we can see our raw measurement, and we can clearly identify here some noisy part of the measurement, around the first half of the measurement, and here we're talking about a so-called interference frequency. Now we can go deeper into this noisy data and take a look at it by using a so-called short-time Fourier transform to visualize our data in the frequency domain. So a short-time Fourier transform helps us to plot the relevant frequencies over time in our signal. I will do this now. So for this we've created a little function which helps us to generate or visualize this kind of plot, this kind of short-time Fourier transform plot. So and here we can see this plot, and we can clearly identify dominant frequency around 500 Hertz, our interference frequency. We can now go deeper in analyzing this interference frequency. For this we can visualize a single time step in a different way, to get a better understanding of the frequencies. Here we use the short-time Fourier transformation function output, as we already did here in this plot function. So and now we can plot the frequency amplitudes or intensities over the frequencies as a bar chart, as we can see here. So here we can see this very dominant frequency, our interference frequency. The same is true for this plot here, the zoomed one. This dominant or interference frequency could now point out to a problem with our machine, for example with a resonating frequency, or a damaged rotating equipment, or even a problem with one of our axis drives. To filter this data, we can define a band, which we will filter in the next step from our measurements, a so-called band stop filter, because we can clearly see here that we do not have a single frequency, but we have rather a range of frequencies which we refer to as interference frequencies. To filter our data, we use a so-called Butterworth bandstop filter, which I will apply now on our data. And then we can plot our data again. And here we can clearly see that the interference frequency vanished. To compare our data before and after the bandstop filtering, we can also visualize our data in time domain again, and here we can see the difference between our raw data and our filtered data. So to conclude, what have we learned? Time series transformation between time domain and frequency domain are standardized functions in Python, so you don't need to write your own functions or buy functions. You can simply use the standard Python libraries. Visualizing data needs some effort to make plots useful, as we have seen, so we need a little effort to generate these short-time Fourier transform plots. But if we have such kind of plot, then it is easily to spot such an interference frequency, which we are interested. And with some extra effort, we can automate all these steps. This is also realized in our Etna health check solution, which I already mentioned. And yeah, we're doing all this to get insights into potential problems with our machines. And we also use this interference frequency detection to prepare our data for following tasks, for example, for automated segmentation, where we have problems with noisy data. Okay?
Maybe I interfere
yes,
for
of course,
a question.
Of course.
Can the frequency analysis tool mentioned be used for additional problems with my machine? Can you give me some examples?
Yes, of course. A very good question. You can use a frequency analysis to detect various kinds of machine problems. For example, you can use it to detect roller bearing problems. You can detect lubrication problems. You can detect problems with process influences. You can detect loose fasteners, for example, or imbalances of the machine. There are some examples for which you can use a frequency analysis. Now we've learned a few things about analyzing acceleration data, but how can we specifically use these gained insights for our machine? Well, as we've shown, for this specific use case here, there's this interference frequency at around 500 Hertz. And one can use this knowledge now to generate recommendations regarding the affected machine. As in this case, for example, optimize the spindle motor controller to reduce vibrations by using these detected interference frequencies. By doing so, we can increase our part lifetime, for example, of the spindle bearing or the guidances, and we can also increase our workpiece quality, for example, in terms of drilling accuracy. So, and as we can see here, after the spindle optimization, as I've already shown, this interference frequency disappeared. And now to conclude, we can use such proactive actions to make early detections of problems possible in order to prevent quality issues or malfunctions of the machine. If you're now interested in getting such recommendations from our EMAG experts, we already have a solution available, the Etna Health Check, as Andreas already introduced it. And our Etna Health Check will provide you with automated condition monitoring and predictive maintenance. And if you're interested, just contact us. I will now hand over again to my colleague Andreas, who will tell you something about calculating takt times and performing a so-called root cause analysis.
Okay, thanks a lot, Patrick, for handing over. Yeah, in the next use case, we want to dig deeper in the data that we directly collect from the machine and try to show you how we can calculate, for example, KPIs in root cause analysis. We want to show you this because we think that even the data that you can collect with the Etna Cortex from the control unit, it's already very rich in information, and you can easily calculate very important KPIs, for example, such as OEE or also the piece quantity per shift, and do some simple forecasts. What we want to show you now for the KPI takt time, or so called cycle time, how you could use the data to calculate it in very easy ways, and also to use the data collected by the cortex to perform some more in-depth analysis, for example, with the root cause analysis to relate system messages with too long takt times. How we can calculate takt times from raw machine data. So here we will use now the EDNA data science pipeline, which I just introduced you before, but before we can really go dig into the data, we have to set up the data science pipeline. First, we have to set up some parameterization of how to we find the REST API from the EDNA cortex and our authentication details, and also how are we mapping the data from the EDNA cortex to the data structure we want in the data science pipeline. On top of that, we also configure the data science pipeline with some asset information, which means we tell the data science pipeline what kind of assets are in this data included, for example, what kind of machine IDs and in which operations are these machines subdivided. So this is what we are doing in the first step. We define all this with these parameters. So here you can see that we get the EDNA cortex details. There we load the asset hierarchy, which we stored in a JSON document, and down there, so I don't want to go into the details because we don't have enough time today, but just that you get an idea what we are doing. Here we define how the data from the cortex gets mapped to some internal data objects. Okay. With this first setup, we can now continue to how we can load and initially pre-process the data. So this is what we are doing here now. We use a module called raw data loader. This we parameterize with the kind of value types we want to load. This is what you can see here. We want to load a runs completed, which is the workpiece count, and we want to load the system messages. On top, we want to set which machines. This is what I did already before. We want to know all the machines that are in these assets information stored, and we also set the date time range from which we want to load the data. So this is the 2nd of October 2019 from 1 p.m. to 3 p.m. So after this parameterization, we hand it over to this raw data loader module and do also some pre-processing, but I don't go into this. And what you can see now here down there in the log, that we loaded now 6 data objects from the EDNA cortex, and these 6 data objects belong to 6 individual machines. So we have now data in our data science pipeline from 6 individual machines. Now, obviously, it's interesting, how does this data look? This is what we're going to do now. So what we have now is like a data set for each machine where we have the timestamp as index. So timestamp means when was this value created. And then we have in the columns the system messages and the runs completed, so the workpiece counter. So now is the question, how can we calculate takt times now out of this? So the takt times we can calculate by in a very simple way if we just take the time between the production of 2 workpieces, and this is what we will calculate now. So this is a very simple way. You can see in this cell below where we just take the difference between 2 timestamps between the production of 2 workpieces and calculate this in seconds. So. And this is now the result, what you can see here. So we have the timestamp of each individual workpiece and the production time of each individual workpiece. And what you can see here, the workpieces, or most workpieces, are produced in like 87 to 88 seconds. And but there is also one bit higher takt time of 106 seconds. Obviously, we can also plot this data. That's also kind of interesting. This is what we can see now here. So this is are the takt times in these 2 hours time window that we picked. And you can see most of the workpieces are produced in this time of 87, 88 seconds. But obviously, there are some irregular outliers. This we know where they're coming from, but there are also some irregular outliers, which could be some important things, so where the machine was not able to produce. And these outliers are of particular interest, which we will dig deeper on later on. Now we just calculated the takt times for 1 machine, but what the beauty of the data science pipeline is that if we, for example, include such a thing like a takt time feature generator, it can calculate the takt times of every machine we have data for in the data science pipeline. And this is what we are doing in the next step. So we automatize this calculation of takt times with this feature generator. This is what we do now, and what we can, for example, do now, we can visualize the takt time distribution of all the machines. So now we have 6 machines, as I mentioned before, and what you can see now on the x-axis is the takt time of each individual machine, and on the y-axis is how often do we get this takt time. And so it's like a classic histogram. And what we can see, for most machines, we have takt times around 90 seconds. but also for most machines we have some outliers above above 120 seconds. These are very sparse, but there are some. So what we want to do now is we want to mark these outliers that are above 120 seconds, and this we we implemented a function in this takt time feature generator where we can do some thresholding of takt time, and this we do now. We set 120 seconds as a limit, and above this limit every takt time is marked as an outlier, and this is what I've done now. You can have a look again at the data. So what you can see now here, we have some individual takt times, and all which are above 120 seconds, for example this is 128 seconds, is flagged as an outlier. So like this is very simple measures. We subdivided our takt times of produced workpieces into outliers and non-outliers. Okay. And yes, this you can also visualize, for example, for each machine again. This is a plot type called box plot, where you show the distribution of takt times in another way. In the x-axis are different the individual machines, and now the takt time outliers are shown in orange, the normal takt times are shown in blue. And this helps a bit to see what kind of data you are working with. Okay, so this was the first part where we could show how can we calculate takt times and also identify already outliers. But now the more interesting part maybe is how can we relate takt time outliers to some, or how can we find causes in the data which for example system messages or errors that were occurring on the machine that could really cause these long takt times and these takt time outliers. And this is what we want to do in the next step. What we do first now is we already loaded the system messages I showed you before, but we want to have a closer look what these system messages are. Unfortunately, this was a German control unit we got the data from, so the system messages are also in German language. But what I can tell you, there are different type of info messages, and also warnings. For example, some warnings are related to automation system, some warnings are related to user input. For example, when a user just opened the front door of the machine or the security door, and so there are any kind of information is in there, and it's quite interesting to explore. And it's I think even like 24, 25 error or system messages that we got, or different system messages that we got in these 2 hours of time. With this information, we want to do now this root cause analysis. And so before I go back into code, I want to show you a principle how we are doing this root cause analysis. So I hope you can see already this little schematic. Yes, okay, perfect. Exactly. So in the first step, what we are doing, we calculate for each produced workpiece the takt time. This is we already did, but then also the time a system message was active or inactive during the production of this workpiece. So this is like shown with these little arrows, these little dashed arrows. For example, the system message 2 was here with this outlier takt time very long active, and also in this one. And this time we want to quantify as feature. And this is one of the features we are generating. And what you can get then here, this is like a feature matrix, so-called. This is like already very technical, so I already say sorry to the non-experts. But this is like the thing data scientists work with, or data analysts work with in their time. But this information, like it was a system message active during the production of a takt time, and was of a workpiece, and was this a takt time outlier as a flag here, goes then into so-called machine learning models, and these models learn dependencies between those 2 variables and these target variables, and for example can give us in the end the influence of system messages and long takt times. Okay. I hope you got the principle of what we are doing next. So in the first step, we really generate these features of takt time, of system message relative to takt time. And this is what I'm going to do in this one. It's a very long one, so I don't go into the details. But we see here in the log it worked. So now we should have different features that calculated the length of the system message activity during the production of a workpiece. Okay, this we use now as input for our model training, and the model training is like this, that we can define models, the model name, the model class. We pick here a decision tree classifier from the library scikit-learn, and also tell the models for which machine IDs the model should work. And the machine IDs we build a model for each of our machines we had on top. And yes, this is what we are doing now. And is what I will run. So we define the models. The model we put into a model training module, and this model training module automatically splits our data sets into training and test data, and does this several times so that we can get a kind of a robust predictor. What we can see now, we have this model was successfully trained, and now we can use this trained model for some in-depth analysis. And the in-depth analysis, what we're going to do now is exactly this plot I showed in the schematic. We now try to infer dependencies between system messages and the takt time outliers. And what you can see here, this kind of feature importance is exactly this importance. If a system message was long active when we had a long takt time outlier, then it also has a strong feature importance. And this is what we can see here. In German it's called Warte auf Werkstückwechsel Schnittstelle 1. It means like the machine is waiting for the automation system to pick up an already finished produced workpiece or bring the raw material for production. So it seems like the main reason for takt time outliers here were really problems with the automation system. We are already at the end of our demo. There's even a question.
Yes, so and meanwhile another question came in. Yeah. What are possible next steps after dependencies between system messages and takt times have been discovered?
Yeah, good question. Obviously, it always depends on what kind of cause you are identifying. So in this case, where the automation system is maybe the reason, it could be that you need to optimize your processes. If this is not like only in this 2-hour time window, but for example, you analyze the data for over a couple of weeks or months, and you see it's always the reason for long takt times. It's the automation system. Then you have to think of what can you do. Maybe you can introduce buffer bands. You can reprogram your automation system, but this is all what you need to discuss also with process experts. In the other case, where you have, for example, a reason which is not frequently occurring, it could be used, for example, if for example during a shift we had takt time outliers, the production was not like planned, then you can use such an analysis directly in the next shop floor meeting to discuss or to have a transparency in what happened in the production line and the machine, and discuss what could be the reason and how to fix it for the next time. And so it always depends what you have to do, but it gives you a transparency what's going on in the line and helps you to decide what's the best next step, I think. Yeah.
Would it be also possible to send the materials which you used in the demonstration?
Sure, yeah, so we can send the material as a HTML file or PDF file, and also be happy to have a quick call maybe afterwards if you're interested in what we did in detail, because it was very fast, I think. So yeah, just contact us and we are happy to send you the details. Okay, if there are no more questions, I guess we will head on. So in this example, we showed you, for example, how to calculate takt times. For a lot of different KPIs, we have standardized apps and applications that are already doing this. For example, we have a machine status monitor which aggregates the stack light information of a complete production line or even a production hall, and shows you, for example, in such dashboards, we have the takt time monitor that can calculate live the takt time during production, and gives you transparency on the performance of your line. We also calculate the OEE from machine data directly at different levels: machine level, operation level, production line level, and also can do some anomaly detection, for example. On top, we also do some forecasting. For example, we do a smart tool change where we make it transparent when the machine user has to go to the machine and switch the tools. So he knows the time when he has to act and could already prepare tools. This is also shown in this dashboard, so that it really makes the production process transparent. And we also, for example, calculate the part quantity that's already produced in the shift, but also forecast it so that everyone knows, okay, with this speed of production we will achieve our goal of production in this shift or not. And so you can manage or you can interrupt early and interfere early with your production process and do some changes if you see it's not working. Yes, but obviously there are not only the standard applications. We already showed you some of the applications. You can also do some more complex things. What we showed you here, it's again the takt time calculation in a bit different visualization. So on the rows are now representing all individual machines of a production line. and on the x-axis is the time. And all each individual column is like one produced workpiece, and the color is like the takt time. In blue, what you see in blue is all takt times that are good, and so the work you don't have to worry about anything. But in red, you can clearly see there are some takt time outliers. And what's interesting about this plot, you can clearly see how takt time or problems at one machine propagate within your production line to other machines. And like this, you can infer interdependencies. So this you can see, yeah, this red lines from all these red columns like propagating from left to right, and this is very interesting to identify, for example, bottlenecks in your production line, do some root cause analysis, and then on top of this, optimization of your production process. This is something very interesting. We are at the end of our use case demonstrations, and for the outro I hand over to Patrick.
Yeah, thank you, Andreas. As Andreas already mentions, we are almost at the end of our webinar for today. So on this slide, we've summarized the three key learnings for today. Data from production machines offer a vast amount of unused potential for valuable insight and production optimization. Analysis of machine data offer the possibility to monitor critical processes, analyze historic machine data to find optimization potentials, allow forecasting and planning of maintenance times and supply chains. And an important aspect, a good analytics framework helps to quickly transform technical and business insights obtained from analysis into usable analytic solution. We are happy if we've attracted your interest, because our EMAG IoT product portfolio will help you building data analytics solutions specific for your challenges and needs. Simply contact us for more information. Yeah.
Many thanks to Dr. Kühne and Mr. Kaiser for the presentation, and welcome back to our audience. As I already mentioned at the beginning, we will now come to your questions. And if there is a question you would like to ask in confidence, you're very welcome to let us know, and then we arrange a one-to-one appointment after the webinar, or contact us simply by mail. So then we are ready and looking forward to your question, and there is already the first coming in. It's about the price range for the machine and system.
Yeah, good question. So here we have to distinguish between new machines and retrofitting machines. But I can tell you for the Aetna IoT Core, so the required hardware, you have to invest 9,200 euros for a new machine and 7,700 euros for retrofitting machine. The corresponding software, the Aetna Cortex, costs you 4,900 euros, and the Lifeline dashboard with data apps costs 450 euros per year and per machine. And our Aetna Health Check will cost you 2,900 euros per year and machine. So that's our current price range or prices for our Aetna IoT solutions.
Mm-hmm. Thank you. Next question. For customers with existing machines, what is the requirement for hardware and software for machine monitoring, machine data, forecast and planning?
Yeah, for customer with existing machines, so the first step I think would be to install the IoT Core and the Aetna Cortex, that you can install that you can collect the machine data, and then it depends what you want, what kind of applications you want. This we can identify maybe together. But for the case for condition monitoring, what we can see here on the left, it's the Aetna Health Check and the Neuron 3DG. You need this additional sensor which gets installed in your machine. And the software, the service, where Patrick already told you what the pricing is.
Yep.
And if you want to go more into this KPI analysis and live dashboards, then we are here with the Aetna Lifeline dashboards and data apps. And on top of this, there are also other applications like that we can identify together and also implement. So, for example, we are looking now in process monitoring and anomaly detection during processes. So just contact us if you're interested, and we find the right solution.
Mm-hmm. There's another question for additional examples of data analysis using machine data.
Yeah, it's a good question. So that there are really a bunch of use cases that you can do with the machine data, and that you can try to answer also with the machine data. That's maybe how to be better phrased. But So one thing, obviously, with the KPIs, you can do already quite a lot of things. For example, one customer side, we identified a lot of problems during shift breaks and also during shift changes. So this is a thing in a fully automatized production line that shouldn't happen. But in this case, for example, sometimes the production line stood still for like 10 to 15 minutes and didn't produce. So what we could see with the in-depth analysis of, for example, the OEE during shifts, and what the customer could do then, for example, he introduced overlapping shift breaks, so that like the first part of the team started the break, then they will overlap, and then the second part of the team went to break, so that the production run smooth through the break, and there were no missed work pieces. Another thing, I already mentioned it in the last answer, is like monitoring of the production process. The production process, for example, and this is very important, for example, to monitor workpiece quality. So the workpiece quality is a very crucial thing, and we had one customer's case where the customer had problems with the workpiece quality, and he had to manually monitor each of the workpieces. And what we did there, we used or we collected high frequency machine data and did some anomaly detection modeling with some machine learning models. And like this, we could the machine learning model then could predict if a tool was like okay or not okay. And like this, the machine user or the manual monitoring could be reduced by 95%. So this was a big advantage for the customer. So that, yeah, a lot of use cases to be done. Yeah.
Mm-hmm. Would it be possible to show the live data screen for cycle time, OEE, etc., and how does it look like?
To get a first impression, maybe you can see it here. Here you can see a live data screen depicting the OEE, takt time, and our health check predictions, I think. Maybe Andreas has some
it's not
better pictures for us.
Yeah. I have some pictures maybe, but not. Yeah, I think it's not too easy to get it live now on screen. Yeah.
But we can provide you with material.
Yes, just contact us and then we provide you with some material afterwards. Yeah.
Mm-hmm. Then we send afterwards. Mm-hmm. You can see here the contact details if you want to contact us afterwards. And then we have now reached the end of our webinar, and I hope you were able to take some interesting impulses with you. Soon you can also find today's webinar on YouTube, where already other webinars are uploaded from EMAG. Once again, I will give you a short reminder for the webinar next week from IoT, directly from the workshop from the machine. And so thank you once again for your participation, and also in the name of our experts in the studio. Take care, and if you want to, until next time, goodbye.